Hi, I'm James Borg, and this is my presentation on coloured noise time series as appropriate models for environmental variation in artificial evolutionary systems. So our motivation for this work was evolution under environmental variation. Evolution is intrinsically linked to environment. Organisms find themselves in environments that are either externally imposed upon them or the emergent results of interactions between organisms and the world, or some mix of the two. But fundamentally, environments change over time and evolution has to react to that environmental change. Um, Evolution reacts to environmental change over multiple timescales, hedging its bets against short-term and long-term environmental change, with the objective of not only maximising fitness in the short term, but also increasing the long-term likelihood of survival. You could argue there's two distinct strategies for dealing with changing environments. One would be to evolve to cope with a broad range of environments, where the other would be to try and specialise within environmental niches or track environmental change closely if possible. In the first strategy, you would expect generalist individuals to emerge who are adapted for a number of environments but specialised for none. This does run the risk of being outcompeted at any given time step by specialist individuals, but does maximise geometric mean fitness. And the second strategy, populations would form of specialist individuals, maximising arithmetic mean fitness, but at the risk of being outcompeted by generalist populations on average over time if the environment is changing. So the nature of the environment and the environmental variation has a fundamental effect on the type and adaptiveness of individuals evolving in that environment. So when exploring evolution via artificial evolutionary systems, either to evolve controllers, to explore open-endedness, to understand evolutionary dynamics, we must consider the nature of the environmental change. In nature, we often see time series, ecological, environmental, geophysical time series, exhibiting characteristics of coloured or 1 over f beta noise. And therefore we here have explored coloured noise and how evolution reacts to noises of various colours. So in order for us to understand the evolution and the coloured noise, we probably need to understand coloured noise to start with. So to obtain the colour of a time series, any time series, this works on any time series that you produce, you can decompose by way of a Fourier transform the time series into its constituent sine waves of different frequencies, as seen in the middle figure here. The spectral density of any of the constituent sine waves can be expressed as 1 over the frequency to the power beta. This exponent beta describes the colour of the noise. So when beta equals 0, this equates to white noise. All frequencies have equal influence on the time series. White noise is also described as Gaussian random noise. You can see on the left-hand figure here that the white noise has the same relative influence per unit frequency for all frequencies. Beta equals 1 is pink noise, or 1 over f noise. And beta equals 2, 1 over f squared noise, is red noise, sometimes also called brown noise or Brownian noise. We'll call it red noise here. As the colour of the noise reddens, higher frequency sine waves become less prominent features of the time series. And we see that here. So under red noise, the higher frequency sine waves are a less prominent feature than they would be under pink noise and under white noise. Now, pink noise falls midway between white noise and red noise. Looking at the right-hand figure, it's also interesting that under pink noise, at any given time step, all frequencies have equal influence on the resulting output. For this reason, along with empirical results from real-world time series, Halley, this is where all the figures come from, Halley's work, argues for pink noise as a null model of environmental variation, as opposed to white noise or red noise, which are the more frequently used types of environmental time series people had used in the past, especially white noise. White noise was very prominent. But it looks like pink noise has fairness over all scales, which is interesting. So this is what some coloured noise time series from white through to black noise look like. So as you can see, as beta increases, the level of what might be called autocorrelation also increases due to the low influence of high frequency sine waves. Essentially, as beta increases, trends and or direction begin to appear in the time series. So when beta equals 200 red noise, this is also sometimes called a random walk. So for white noise, each point in the series is independently set from a normal distribution. So there's no relationship between time steps at all, which means that the environmental mean, the mean of the time series, remains stationary as well. Red noise is essentially just a random walk, and what you see is these general directions with perturbations. But there is a strong relationship between time steps. So recent time steps affect the current time step state quite heavily. Black noise is a more extreme example, though it does appear in nature in geophysical data sets. Each time step is now very heavily influenced by the directly preceding time steps, with very few perturbations at all. Pink noise, which is often thought to be the more interesting form of coloured noise, is seen very frequently in ecological environmental series, such as temperature time series, often show pink to red noise characteristics, and also population sizes. If you were to look at a population size dynamics of lots of wild populations over time, you see time series that look like this. General growth, but with large growths and drops, but general directions of changes. All of the time series that aren't white noise are non-stationary, so we do get a change in the mean over time, which means the variance over the time series does grow. Though often when modelling these coloured noise time series, you normalise all time series for equal variance in order to remove that effect. So the model implemented here is relatively simple and self-explanatory. We have a population of 1,000 individuals. All individuals have a genotype with 2 loci, which are essentially just the mean and standard deviation of a normal distribution. Fitness is calculated using a Gaussian function. So we look at what the environmental state is at the time step, and then we look at each agent's mean and standard deviation. And given that mean and standard deviation and the environmental state, we calculate the fitness based upon the Gaussian function that's produced. A tolerant or generalist individual would have a larger standard deviation, resulting in a lower maximum possible fitness if they exactly match the environment, but a wider range of environments in which they can achieve some value of fitness. Specialised individuals would have very low standard deviations, which would mean that they get very high fitness if their mean matches the environmental state, but they would have very low fitness if the environmental state moved outside of the range of their normal distribution. Reproduction in this model, we remove the least fit 50% of the population, and then we use asexual reproduction to replace them via fitness proportionate selection. Mutation is applied simply by adding some Gaussian random noise to each of the phenotype positions. So our first set of results are in regard to populations tracking the environment, so the mean from the individual genotypes. And these are just example plots over the first 2,000 time steps. So in regard to populations tracking the environment, what we see is what we'd expect to see very much. White noise is too noisy for evolution to effectively track, but because the environmental mean remains stationary, evolution resolves to the environmental mean. Red noise at the bottom here, with its lower magnitude step changes from time step to time step, is much easier for evolution to track. Pink noise falling somewhere in between. We do get some ability to track the general direction of the environment, but it is too noisy for perfect tracking. And this is what you'd expect to see in these kind of environments. Another way of looking at the results is also to look at the tolerance as well as the fitness of the agents in the population. Tolerance being dictated by the standard deviations in the population genotypes. And these results report over the entire simulation length for all repetitions of the model. So as the exponent beta rises, the environment reddening, fitness, which is the ability to track the environment, does improve and becomes less variable across populations. Tolerance, on the other hand, shows a trend towards lower tolerance and greater specialisation as the environment reddens. So what we're seeing here in this top figure, what we're seeing here is a greater ability to track and specialise for the environment. This isn't possible at lower exponents, resulting in a pressure in favour of greater environmental tolerance. So white noise environments, you need quite large levels of tolerance in order to ensure that you get some fitness as the environment changes. But in red noise environments, this isn't necessary because as you can track the environment, you don't need to be very tolerant, so you can maximise your fitness instead. In pink noise environments, falling midway between both, we see this kind of payoff between, or this balance between specialism and generalism. And the sigmoidal shape of the tolerance curve is interesting and suggests something interesting is happening at the range of exponent of 0.5 to 1.5, the general pink noise range. We can investigate the sigmoidal shape of the tolerance graph a little bit further by taking the first derivative of the tolerance. And from this we can see that the greatest change in tolerance occurs at exponent equals 1, at beta equals 1. This is pink noise. We also see a little change occurring at white, exponents less than 0.5, and red, exponents higher than 1.5, noise, indicating that pink noise, this exponent range of 0.5 to 1.5, is a transition point between selection for generalism or tolerance at white noise and specialism at red noise. This begins to shed light on why pink noise might be a special case and a good candidate for a null model of environmental noise. It promotes both specialism and generalism, so plasticity and tolerance, while still trying to maximise fitness. So there are a number of takeaway points really from this work, but the major ones really are that the colour of the environment does profoundly affect the evolutionary response. Evolution is heavily tied to the environments we use, therefore we should think heavily and carefully about the environments that we are using in our models. And coloured noise time series, especially pink noise time series, are frequently found in nature. Therefore, coloured noise does act as a good candidate for a null model of noise that maybe we should be applying in artificial life. It's environmentally justifiable. We can vary beta and look at the effects of beta. And there's a possibility of getting both generalism and specialism out of our models and pushing forward the dynamics of our models. I'd like to finish by thanking my collaborators, Matt Grove from the University of Liverpool and Fiona Polak from the School of Computing Mathematics at Keele University. Please feel free to email me any questions that you might have.